Now this is seminar 13, and we continue to solve this problem that we started to discuss during the lecture. The integral from -1 to 1 e to x. Yes, and if we gather these two integrals together, we will get the following. So opening the brackets, we will get y prime squared plus 2y prime v prime plus v prime squared plus 6y squared plus 12 yv plus v squared minus y prime squared minus 6y squared dx. Okay, we can eliminate something, so this and this and this and this. So we have this sum. I will rewrite it as the integral from -1 to 1 e to x, then 2y prime v plus 12yv dx plus the following part. So we have these two functions, e to x times v prime squared plus v squared dx. So we want to prove that this is greater or equal to 0. If we prove this, then we are done, because this will prove that y is a minimizer, because for any function v satisfying the condition v of -1 equals v of 1 equals 0, we will have that this difference is non-negative, so y is a minimizer. Yes, so this part is positive, yes, non-negative. So if v is an arbitrary function, we can see that this is greater than or equal to 0. And now let's discuss this part. Okay, we must prove in some way that this is non-negative. How to do this? Let's look at this integral, e to x times 2y prime v prime plus 12yv dx. I want to apply the formula of integration by parts to this term. So I will rewrite this as -1 to 1 e to x times 2v prime dv, okay, plus the last part of the integral, e to x times 12yv dx. Okay, then using the formula of integration by parts, we rewrite this part as the product 2y prime e to x v from -1 to 1 minus the integral from -1 to 1. Okay, and then the derivative of this part. We must take the derivative of this part. It will be e to x times 2y prime plus e to x times 2y double prime dx plus, and we rewrite this part. Then what about this part? If we substitute -1 and 1 into this function, what shall we get? So let's substitute 1. What is the value of this function at the point 1? Do you know? The value of this product, y prime e to x times v at the point y, or 1.
1 doesn't matter because
-1 doesn't matter, and 1 is also doesn't matter, because we have this condition. For any variation v, we must have this. Yes? And so if we substitute 1 for x into this expression, we will get 0 here. V of 1 is 0. Then this part is 0. Yes, this is 0. And for -1 also. And we're left with this equation. So this expression. We will get e to x times, and now we will join these two integrals, and we will get 12yv minus 2y prime plus 2y double prime dx. But this is exactly the same as this equation. So this equation, or this equation, yes, it is 0, because we have found the function y. So from this property, from this equation, yes, this is the equation for finding y, yes. And so we can see that this is 0. This is 0. Well, and so we have proved that this part is 0 and this part is greater than 0. So it is non-negative. Okay, is it clear how to prove that the first part is 0 or not? So this one, yes. So we have written the difference of this function. Okay, so we want to prove that our function y, so let it be, so y is the solution, is our given function. I don't want to substitute this expression for y, but we have in mind that y is our solution. So we may use some maybe bar or, yes, and tilde. So y tilde is this function, yes? So next we write the difference. So this is j of y tilde plus v, yes, if we use tilde, minus this expression. And we know that y tilde satisfy this equation, or this equation, yes. It was found from this equation. Okay, next, the difference. So we're trying to simplify this difference. Some terms are eliminated, yes. We write this as one big integral. We gather all the terms together, yes. We cancel similar terms, y prime squared and y prime squared and so on, yes, simplify. And we can see the positive part, some positive part, yes, and this part corresponds to the part, corresponds to this equation, yes. The last part can be rewritten as this equation, as this equation. The idea is the same as it was when we have obtained the Lagrange equations. The idea is integration by parts. Integration by parts.
How did you combine the term with dv, integral with dv, and the integral with dx?
Integral with what? dv, v is the last line. Okay. And where is dv? Right. In just a moment. It must be. So on this one, and so this must be multiplied by v, because this is the formula of integration by parts, yes. So thank you for this. So we must multiply by v. So by the formula of integration by parts, so this is rewritten in this form, integration by parts. And now we have v. And we can combine them, yes, and so I missed the multiplication by v. So dx, we must multiply by v. And so this is our original equation, Euler-Lagrange equation, and it is 0. Okay. So this is so we can prove that our critical function, the critical function for this functional is actually a minimizer. So this is the way to prove this, to check this. Okay, so do you want to try to solve something? Okay, I will help you. So task number 2, let it be task number 2. The integral from 0 to 1, x y squared plus x squared y prime plus 1 plus x squared y prime squared dx. We must minimize this, and the boundary conditions are the following. Okay. Well, so the first step is to write the Euler-Lagrange equations. So dy over dy, yes. So dl over dy first.
Okay, we have y here and here. So this is 2y plus
Yes, correct.
and
dl over dy prime.
so x squared y plus plus 2 times
Yes.
dy dx of is the full derivative of this. So it will be 2x y plus
Yes.
square
Y prime, yes.
plus 2y prime 1 plus x square plus 2y prime 2.
Correct.
These should be equal to
Yes.
to 1x plus x square y prime. Now we should simplify.
Yes. Yes. And the second, yes, the second x squared y, and yes.
So it means 2y double prime 1 plus plus 2y prime 2x is equal to 0.
Well.
Okay.
Now
this is a differential equation.
Yes, and we must first find y prime and then prime. So the function y prime. So we can make a so we may introduce the new function y prime. Let z be y prime. Yes.
Okay. So this can be written as z prime 1 plus x square
Yes.
plus 2z is
Yes.
equal to 0.
And the variables are separated.
Yes. Okay.
Minus. Correct. And then z prime should be rewritten as dz over dx. Dz over dx. Yes. Correct. Dx. Then integrate. Yes.
Z is equal to minus
Okay, then ln z equals this. Ln z, and after this we will
z.
so not z but ln z, and after this we will eliminate the logarithmic functions. Yes, so that is z is equal to
Plus
1 plus c. Yes.
So z is equal to c divided by
1 plus x squared. Yes. Exactly.
Okay.
And after this,
This
so
is
we
y prime.
this is y prime, and so next find y. Just integrate. Yes. You need not solve the equation. So this is the same to solve the differential equation or to integrate. Yes. Integrate.
Okay, this is
Arctangents or tan inverse. Yes. Yes. Well, it's this. And then
y.
find C1 and C2 using initial conditions. Yes.
Okay, so the first initial condition is 0, 0.
0, 0, yes.
Tan inverse of 0, 0.
Tan of 0, arctan of 0 is, yes, C2 is 0.
The first condition and the second condition will give tan
Yes,
Not
plus
right,
0.
plus 0.
Yes.
Okay, so we know y equal to 4 over pi.
Yes, this is correct.
Now,
Okay, and after this step number 2, I will help you with this step number 2. So next we must find the difference. So this is step number 1. Let it be 1, and then step number 2. Yes. Step number 2. To find the difference, and so after simplification, we should use this equation. So we should obtain this equation as a part of this difference. We will obtain this. Yes. So substitute y plus v for y in this equation. Yes, in this. So just rewrite the integral with the substitution y plus v for y.
Okay.
Yes. Okay, so this is a good idea to write only the expression, the integrand, without the integral itself. Yes, we will use the integral later. Minus, the integrand depending on y. Okay, so a good idea, yes.
Now over here,
Yes.
you can say x times 2 vy plus
Yes.
v square, and over here also plus x square. These ones will cancel out, so and over here
Yes. Okay, and usually in this expression, so I will take a chalk. Usually in this expression, we can see the variables of the form 2vy. This term will go to the Euler-Lagrange equation, and we must separate. I will use. So v squared and v. So it is. I think it's v squared or v times v prime. Yes. And this will go to the other term. Yes. We should collect these terms, and so the underlined terms, yes, this and this should be collected to form the Euler-Lagrange equation, yes, and these terms will give us some other part. Let's do this. Let's collect them. So consider this part separately and the other terms separately. And why? Yes. Well, so you have collected terms of type 1, and then for terms with v prime, yes, so for this and this.
this is not v prime.
So and what is it is v or
Just v.
Yes, so it is not prime. Yes, vx squared y prime. Yes, so then we will leave it. For these two terms, we should use the integration by parts. Yes, because we must go to v, then v will be the common factor for all these terms, and after factoring v, we will get the early Lagrange equations inside. Yes. So apply the integration by parts for these terms, these two summands.
So it is x square y plus 3 times plus x square
Mm-hmm.
y dash
Mm-hmm.
v
Mm-hmm.
dash
Yes, dx. And from the integral from 0 to 1, from 0 to 1. The limits of integration from 0 to 1. Then integration by parts, and you should move v prime under the differential. Y prime, well, yes, multiplied by v. And subtract, yes. Derivative of this.
Okay.
Yes. Yes, from 0 to 1, correct.
And 0 to 1. Okay, we'll substitute.
So this is 0, yes, because v of 0 and v of 1 must be equal to 0, so this part is 0. And then this must be combined with these two, with which terms? With these terms to obtain the earlier Lagrange equation. Yes. 2vxy plus will be 2xy plus x squared y prime. Minus that part. The part
Now
there.
this is all. This was also.
And v without v, I think v must be factored out. Yes, so v must be here. And minus all these terms, minus 2xy and so on.
Then there will be an
Yes.
integral.
The integral, yes. Yes, next we should cancel out some similar terms. Like in Lagrange equations. Yes, and this is just the Lagrange equation. Yes, 4, but not 4. Why 4? Maybe not 4.
Yes, it's 4 because there are 2 2's.
2 times, yes. 2 and 2, yes, 4. It is 4. So the same, yes. It must be the same.
This is 0.
Yes. Yes, this is 0 by virtue of L Lagrange equations. Yes. Yes. And we have some positive part. Why is positive? It is so. We must prove that it is positive. X v squared plus x squared. Yes, x times v squared plus x squared v prime, and plus 1 plus x squared times v prime squared. and we must prove that it is positive for any function v, right? For any function v. Let's try to prove this.
Okay.
So because this may be negative, yes, it may be negative. So this expression may be negative. And how to prove that? So the total is positive. Maybe to estimate this in some way.
Okay.
Yes, something like this, I think. Yes, or just multiply by, so it looks like, so I see that, so if we replace this by x squared, maybe, is this x squared or not? No, yes? So, but if we rewrite it as x squared v squared plus x squared v prime plus x squared v prime squared is always greater than or equal to 0. Yes, because this can be rewritten as v squared plus v prime plus v prime squared. Yes, so this is always positive, not negative. This term is not negative. But we have, so then after extracting this positive part, we have x minus x squared, yes, x minus x squared times v squared plus v prime squared. So our expression, this one, is the sum of this part, which is non-negative, and this part. Yes? So if we add them together, so let's add them together, we will get this. Yes? So this expression is represented as the sum of this. So I will remove, so I think, so, it is not correct. So if we add these two, we will get this, I think. Yes? Am I right? Right? So the sum of this will give us this term. This is just this. And the sum of this will give us this. Yes?
Okay, now we just need to show that
this is non-negative. Yes, because x is between 0 and 1. Yes, so this is non-negative. Of course, yes. And so proved. So I think it's not an easy way, yes, but this is the rigorous proof of that our function y is a minimizer. Yes, thank you. Sit down, and who wants to continue?
So what if we prove that not greater than or equal to 0, it's less than 0?
So
if it's less than 0, then what happens?
That
means our function.
Yeah, so of course, usually, so people do not do this in this way. So now we have learned only the necessary condition, and so we use some immediate method, and it is a long way to prove that this is a minimizer. Usually,
No, to prove it's a minimizer, we need to
Yes.
prove it's greater than or equal to
Yes,
zero.
yes, yes. To prove that this
Okay.
difference is greater than 0. Yes,
If-
greater than or equal to
If we
0.
see that it's less than 0, then what?
Or if we see that for some functions it is less than 0 and for some functions it is greater than 0, then it is a saddle point. Then it is a saddle point. If we see that it is less than 0
For all
for any function v, then it is a maximizer. Yes, maximizer, because this is
Oh yes, yes.
so this is the greatest value. Yes.
Okay.
The maximizer. Sometimes we are asked to find the maximizer, not minimizer. Yes, and so this will be the solution. Okay, now let's consider the next. Okay, I think it will be the last. Yes, yes. So very long way to, yes, very long solution. These problems are not easy. Yes. So the last will be the integral from 0 to pi half.
Not trigonometric.
Not trigonometric. Squared minus y squared plus 10y times e to 2x dx to minimum y of 0 equals 1, y of pi half equals e to pi. So it is not minus plus 2x. Something on the board. Yes. Dy prime, yes. Yes. Then equate these expressions, yes. Minus, yes, then divide, yes, of course, yes, divide by negative 2.
Oh, actually, this is my negative 2, so we can divide by negative 2.
Why?
Oh,
Minus 2, we can divide, yes, it will be 5. Well, how to solve this? Do you know? This is a linear equation with constant coefficients, linear non-homogeneous. So you should move 5e to 2x to the right and then solve y to prime, yes, plus y. Oh, but it will be trigonometric. The solution will be trigonometric.
First, the homogeneous part.
Yes, the homogeneous part.
once we're done with the homogeneous part, what next?
Yeah, so it will be lambda. No, so plus 1, and there will be complex roots, right? Complex roots.
Ah, mistake.
Plus 1.
Sorry.
Mm-hmm.
I forgot it's not Wi-Fi.
Mm-hmm. Okay, I'll check them. Just a moment. Uh-huh. Mm-hmm. Okay, so the linear combination, so you needn't do this. So if we have complex roots, then it will be the linear combination of x, y, so cos x and sin x. You need not write it in this form, just c1 times cos x plus c2 times sin x. So this was used in proof that this is correct, but we need the real part, yes, not the complex part. We need to write this. So next, the non-homogeneous part, a particular solution, right, can be written in the form. So what is the form for the particular solution?
So
Like the right-hand part. So the constant times e to 2x.
this.
We should seek a particular solution in the form a multiplied by e to 2x. Yes. Y particular will be a times e to 2x, where a is an undetermined coefficient. For a multiplied by e to 2x, you missed e to the power 2x, not a to the power, but e to the power 2x. Okay. Next, you should substitute this into the original equation and find plus, yes, and equate. Yes. Yes. 5a is 1, correct. And so a particular solution is e to 2x. Yes. And this is the plus e to 2x. Yes. Next, you should use initial conditions. Yes. Substitute 0 and substitute by half. And substitute so 0 for x, so we will get, so we must substitute 0 for x, yes, and so plus 1, and c1 is 0. Not 1. You must substitute, not 1 here, because you must substitute pi half for x, yes, e to pi. Not pi half, multiplied by 2, because the power, the exponent is 2x. Pi. Also 0. So no trigonometric functions. Right. So this is our function, so our minimizer, and now we should check that it is. So this is a critical point, and we must check that this is a minimizer. Yes. Okay, just rewrite. You will use yes. Yes, and subtract. I'll remove what. Yes, correct.
Square.
Minus 2yv. Minus. Yes, plus 10v. Plus v. Yes. Minus v squared. Yes. Plus. V. 2x. Yes, I think it's correct. It's correct. And now we should combine which terms? These linear terms. Linear with respect to v prime and v. Yes, and this. And so we should consider separately this linear part. Let's treat this 2y prime. Let's rewrite 2y prime. So 2y prime v prime minus 2yv and plus 10v e to 2x. This is the first part. And the second part will be v prime squared minus v squared. And I will explain how to treat the last part, so we can see the difference of functions, but it is possible to prove that the last integral is positive. Yes, so I will show how to do this. So from 0 to pi half, yes, pi half, and from 0 to pi half. First, let's consider this part and prove that this is 0. We must prove that this is 0, and to do this, we must rewrite. We must eliminate, or we must apply integration by parts to the term containing v prime. Yes, and after this we will get 0. We will get Euler-Lagrange equations from this.
Bring 2 out.
Yes. What's this? What is u? What is u? U is just integrate by parts. Yes. So the integral of minus y prime v prime. Yes. If you want to integrate by parts, you must move v prime under the differential and so equals. Yes.
Wait.
How to? Okay, so only this we must integrate this. So it is minus, I think. Is it minus or not?
No.
Or not? Not minus. Not minus. So not minus. Next, to integrate by parts, you must rewrite it, move v prime to the under the differential, rewrite it in this way, yes, and then switch these functions. So equals integration by parts.
I just want to do it my way. It's going to be equal to uv.
Yes, this is u and this is v. Yes, so I see u and v. Right. So not prime, but just v, because u. So the formula of integration by parts is u dv equals uv minus the integral v du. So if we move v under the differential, we will get just v, not v prime. Yes, uv. Yes. By half. Yes. And so v, yes, so v, just v, and differentiate this, so y double prime dx. Okay, clear? So switch u and v, yes. And so the limits from 0 to by half. And so since v is the function such that v of 0 equals 0 and v of by half is 0, so v is this function. So in this difference, yes, v we may substitute, because we fix the endpoints, yes, and so we consider only, we may substitute only the functions for which so all these functions are such that y of 0 is 1 and y of pi half equals e to pi. And y must be this function. So y of 0 is 1 and y of pi half is e to pi. And also y plus v, since we're able to substitute it here, then it must be y plus v of 0 equals 1. Yes, and y plus v of pi half is also e to pi, because we only consider only the functions satisfying this equation, these boundary conditions. And so this means that v of 0 is 0 and v of pi half is 0. Yes, and so we can always use this. Yes, yeah, this is 0. And we can replace that term, the first term, the underlined term, by this.
Okay.
And this will lead us to the Euler Lagrange equations. Yes, and the last part is to prove that this part is positive, is non-negative, and so it is rather difficult, and I will show you how to complete the proof. Yes, so you may so this what about this part? So this is the Euler Lagrange equation. Just must be the Euler Lagrange equation. Yes, it is equal to 0. Yes. Okay. Thank you. And for the last part, we must do the following. So now let's consider this part. And the fact is the following: if v is such that v of a equals v of b equals 0, then it can be stated as lemma, that is the lemma. Yeah, so the integral from a to b, v squared dx is less than or equal to b minus a squared over 4 times the integral from a to b v prime squared dx. So this can be proved using the Cauchy-Bunyakovsky-Schwarz inequality, okay, or Hölder inequality. So I will prove this. Yes. So first of all, I will show. So the first part is if only v of a equals 0, then I will show that the integral from a to b v squared dx is less than or equal to b minus a squared, the integral from a to b v prime squared dx. So this is the first part. After this, I will use the property that v of b equals 0, and I will prove the so the statement of lemma. Now let's try to prove this. Okay, I will do the following. So I will represent v of x, as the integral from a to x v prime of t dt. Well, am I right? Yes. So this is by definition of the derivative and the integral. Yes. So this is our common property. V squared. What is v squared? Is the integral from a to b v prime of t dt squared. And by Hölder inequality, or maybe Cauchy-Bunyakovsky-Schwarz inequality for inner product, it is less than or equal to, so this is 1. Well, the integral of from a to b of 1 squared dt times the integral from a to b v prime squared dt. So let it be, so it is not from a to b, but it is x. Yes, it is x. And this can be computed. This integral is equal to x minus a. Well, and multiplied by the integral from a to x times v prime squared dt. Now I want to estimate this. Yes, I want to, in just a moment, next I want to, well, it is less than or equal to, so this part x minus a is less than or equal to b minus a, and the last part is less than or equal to the integral from a to b v prime squared dt. Well, next I want to integrate from a to b v squared dx less than or equal to the integral of that part. Yes, since this function is less than or equal to this constant, then I want to integrate this. If I integrate the constant, this is the constant function. Yes, this is the constant. I must multiply by the length of this integral, so less than or equal to b minus a squared, the integral from a to b v prime squared dt. Okay, so this is just what I want. Yes, this is this statement. It is proved. This statement is proved. Okay, and now how to obtain this constant b minus a squared over 4? I have used only the condition that v of a equals 0, but I haven't used the condition that v of b is 0. Yes. Now I will do the following. So I will use this condition. So I will remove this, I think. Now I will divide the segment from A to B in half. So it will be A plus B half. And so using the fact that v of A is 0, I have the following. The integral from A to A plus B half v squared dx is less than or equal to, so b minus a, then, so if I subtract from the lower limit from the upper limit, I will have b minus a half squared times the integral from a to b, a plus b half v prime squared dx. And from the condition that v of b equals 0, I will get the similar statement. The integral from a plus b half to b v squared dx is less than or equal to b minus a half squared times the integral from a plus b half to b v prime squared dx. And if we add the left-hand sides and the right-hand sides, we will get the required property, this one. Yes, that. So this proves this property. Yes. Now let's try to let's apply this lemma to our case. We know A and B, and we can estimate the integral using lemma. We have the following. The integral from 0 to pi half v squared dx is less than or equal to, so divided by 4, it will be pi squared divided by 16. Yes, the integral from 0 to pi half v prime squared dx. So now we need to prove that this constant is less than 1. Yes, since this constant is less than 1, yes, then this integral is positive. Yes. Because this is greater than or equal to the integral from 0 to pi half v prime squared minus pi squared over 16 v prime squared. But this is positive. Yes, but this is positive, and so this proves that it is. So we are done. Yes. Not easy, of course, but this is a very important topic. Yes, calculus of variations. So we will continue next time, next week.